Welcome to EDU World Space.
So here's a problem that is quite involved and requires math and physics to get the right answer, right? Uh, and so the setup is as follows. Here is the Earth, pardon the bad drawing. Uh, there's a clock at the equator, which I will denote by E. It's an atomic clock, so it's a very accurate clock. And then you have another clock here at the very north point, so the North Pole, which I will denote as N. So you're asked how much these clocks will be out of sync once 2 years of actual time has passed. And the main idea that we're going to use here is the fact that the Earth rotates, right? And so rotation will cause different uh, will co- will basically have different effects on different parts of the Earth. So if you're on the poles, you're not rotating at all. You're on the North Pole or you're on the South Pole, the Earth's rotation uh, is not uh, does not affect you, meaning that you are at rest essentially. So the North Pole clock is a rest frame. All right, but if you're on the equator, you're rotating at the exact rotation velocity of the Earth because you're at the center of the sphere, right? So this is a moving frame of reference. So this is how we're going to set this up, is that the equator is the moving frame, North Pole is the rest frame. And so before we move any further, we need to know the rotation speed of the Earth, right? And the rotation speed is given by 2 pi, that's the number of radians of a circle, times radius of the Earth over time taken for a whole rotation. So this would be 1 day, 1 Earth day, just to say 24 hours. This value is quoted in the book as 6.38 times 10 to the 6 meters, or roughly about 6,400 kilometers. That's the radius of the Earth. Okay? And so we have 2 pi times 6.38 times 10 to the 6 meters over 1 day, which is 24 hours, times 3,600 seconds in 1 hour, because remember, we want this in SI units, and so second is an SI unit, hour is not. So here's how we cancel that out, and we get Earth's rotation velocity as 464 meters per second. Okay? Note that this is much, much smaller than the speed of light, which is 300 million meters per second. And this will come, and this is why we need a binomial expansion in this problem to begin with. And I will talk about that in a second. So first, let's remember the time dilation formula, which is 26-1a equation. And it says that delta t, or in this case, the rest frame delta t, so that would be delta t sub n to denote, to mean the North Pole, is equal to gamma times delta t e, which is the moving frame, which is to say the equator's time measured time. So you rearrange that, you get delta T E is equal to delta T n over gamma, which is equal to delta Tn times 1 minus v squared over c squared, right? Here is where we use the binomial expansion. And this is straight out of Appendix A in the book. Equation A5 tells you that 1 plus x to the nth power is equal to 1 plus n to the x, n times x, sorry, plus n times n minus 1 over 2, and so on. Now, very importantly, when x is much, much less than 1, this whole thing simplifies to 1 plus x to the n is approximated, can be approximated very well to 1 plus n times x, none of this other stuff here. And this, of course, is equation A6 in the book, in the appendix. So you have that. And notice that we have 1 plus something to the power of something here, in here, in the time dilation equation. So what we have, therefore, is that, let's use a different color. This is just 1 minus v squared over c squared. Let's write it like this, 1 plus minus v squared c squared. And all of that is inside of a square root, which means it's raised to the power of half. And look, this form is very similar to this form. X is just negative v squared over c squared, and n is just half. So that's great. And very importantly, x much, much less than 1 applies here because v is much, much less than c. As we know from here, it is many orders of magnitude less than c. So this is good. This holds. And so what we get, therefore, is that 1 minus v squared over c squared raised to the 1/2 is approximately 1 minus v squared over c squared times 1/2, right? I can write it as 1 minus v squared over 2c squared. So this is what that becomes. So we have that. So we have the time. V we know, C we know. Delta T sub n is something we don't know. It is something we do know, excuse me. This is 2 years. What we want now is the difference. The difference in the reading on the two clocks. So this would just be the rest frame time, which is delta Tn, because remember the North Pole reference frame is the rest frame, minus delta Te, right? And so you have delta Tn minus delta Tn from here, delta Tn times 1 minus v squared over 2c squared. Awesome. And so you notice that a delta Tn factor cancels out, and so you're left with delta Tn times v squared over 2c squared. And we're given that the time that has elapsed is 2 years. V, as we found here, is 464 meters per second. Square that thing. Over 2 times speed of light squared, so that's 3 times 10 to the 8 meters per second squared. And but then you have there's another thing you have to do. The meters per second factors cancel, but then you have something in terms of years, and we already can see that it will be a very large number, a very small number because of a large denominator and small numerator. So we multiply this by the conversion from years to seconds. In fact, 1 year is equal to 3.16 times 10 to the 7 seconds. Seconds per year. So that's your conversion, and that helps us get rid of the years. And what we end up with is something very close to 7.5 times 10 to the negative 5 seconds. And if you remember your prefixes or prefixes, this is about 75 microseconds. So in 2 years, the two atomic clocks will be off by 75 microseconds, which may sound like not very much, but for atomic clocks, it is actually not negligible. But there you go. That's how you do it. Some math involved here, but once you knew how to make this expansion work, it actually turns out to be very simple. So